Let's do a little review on covalent bonding. As established before, covalent bonding is considered to be an intramolecular force of attraction. That automatically means it is a strong force of attraction. Let's take a look at what covalent bonding is, and the definition for it is that it looks at the forces of attraction between nuclei, where nuclei contains protons. So we're looking at the force of attraction, which is the nuclear force for shared pairs of electrons. Remember, when two nonmetal atoms bond covalently, they will share their valence electrons. These shared valence electrons are what we call shared pairs of electrons. So for example, if we look at chlorine, right, that's a Cl2 molecule, each chlorine atom will supply one electron or one valence electron such that the two electrons will form a shared pair of electrons, and this is what we call a single covalent bond. Later we will look at double and triple covalent bonds. For now, what I want to emphasize is that covalent bonding is a strong intermolecular force of attraction which looks at how the nuclei of the nonmetal atoms are attracted to the shared pair or pairs of electrons. We also established that it's a strong intramolecular force of attraction, and we define what this word strong means by saying that it takes a lot of energy to break these forces. So let's talk about covalent bonding in terms of shared pairs of electrons. So if we have one shared pair of electrons, meaning each atom contributed one valence electron, this gives us one shared pair of electrons. This shared pair of electrons is also called a bonding pair. All right, so I'm just going to call it 1 BP, one bonding pair. Where we have two shared pairs of electrons, meaning each atom contributed two of their valence electrons. Right, this gives us two bonding pairs. All right, and I'm going to add in another terminology after. I'm just going to call this 2 BP. Right, of course, where we have three shared pairs of electrons, we're going to call that 3 bonding pairs. Right, so in the CSEC syllabus, we would have been introduced to something called single, double, and triple covalent bonds. So what we're going to do here is I'm also going to describe my one shared pair as one single covalent bond. Where we have two shared pairs, that means it's a double covalent bond. And where we have three shared pairs, that would be a triple covalent bond. Okay. In addition to describing shared pairs of electrons, which are considered to be bonding pairs or covalent bonding, we must also mention the electrons which do not take part in bonding in the outer shell. Right, so these electrons are what we call non-bonding electrons, and we also look at them as pairs of electrons. So these non-bonding pairs of electrons are referred to as lone pairs as well. So if I'm looking at a molecule of chlorine, what I will see is one bonding pair and each chlorine atom has 3 non-bonding pairs or 3 lone pairs. Right, so in total, I should have 1 bonding pair and 6 lone pairs. Right, so I'm just going to draw it in where they are located. Right, so here we have 1 bonding pair, right, and on the outer shell, I should be able to see 1, 2, 3, 4, 5, 6, 6 lone pairs of electrons. So we have clarified what is shared pair of electrons in terms of covalent bonds. I want to further go on to define what is a covalent bond in terms of atomic orbitals and a new concept called molecular orbital. So we say that a covalent bond is formed when 2 atomic orbitals overlap. Let's break that down in a way that we understand it. We just looked at the fact that when 2 valence shells overlap, 2 single electrons will come together to form a shared pair of electrons. We are going to examine it a little more closely by saying that this electron belongs to an atomic orbital. So we've looked at our definition of atomic orbital, and I want to go over it once more before we continue, where we have described an atomic orbital as a region of space representing, right, the highest probability of finding an electron. Right, so this atomic orbital represents some sort of charge cloud. Right, when I say charge cloud, it's an electron charge cloud. We look at the density, right, or the volume of space, and this represents our probability of finding an electron. So when we say covalent bonds are formed when 2 atomic orbitals overlap, right, this is just redefining the terminology from the layman's terms of saying 2 electrons pair up, right? What would happen is, as the 2 neighboring atoms approach each other, there would be overlap of the valence shell. This overlap of the valence shell, looking at it in terms of the perspective of the electron, it really means a covalent bond forms when 2 atomic orbitals overlap. We say that when atomic orbitals overlap, we can't just call them atomic orbitals anymore. They are not, it's no longer an atom, it's a molecule. So what is formed is something called a molecular orbital. We would expect when 2 atomic orbitals overlap, why is it that I am saying a molecular orbital forms? So what this really means is when atomic orbitals overlap, we're actually saying that molecular orbitals form. When atomic orbitals overlap, we say that we get molecular orbitals forming. So we're going to get something called a bonding molecular orbital, and we're going to get something called an anti-bonding molecular orbital. We say that when 2 atomic orbitals overlap, right, a bonding molecular orbital, so that's a bonding MO, and an anti bonding molecular orbital is formed. All right, so let me stick that in there. Oh, an anti-molecular orbital is formed. So I'm looking at my diagram below. And it shows us what this means. So I'm looking to the left where we see two hydrogen atoms. Remember, a hydrogen atom would have one valence electron in its outer shell. Each valence electron would be in a 1s subshell. So I just mentioned they're in a 1s subshell. Right, so that's one electron each. We say that when these two hydrogen atoms approach and the two atomic orbitals overlap, what we will get is something called a bonding molecular orbital. The bonding molecular orbital, as you can see, is lower in energy, and this means it's more stable. So I'll explain this in layman's terms. Where we have two isolated hydrogen atoms, why would they bond in the first place? They would bond if they form a molecule which is more stable. So in forming a molecule, this means we have overlap of atomic orbitals, and that bonding molecular orbital is said to be lower in energy. So in my diagram, in terms of energy, I'm drawing my bonding molecular orbital a little lower. We also have to establish that if two atomic orbitals overlap, we have a bonding molecular orbital which represents the highest probability of finding this shared pair of electrons. And that is what a bonding molecular orbital is. The highest probability of finding a shared pair of electrons. Another concept to wrap your mind around is that there must be a region of space where we would not find the shared pair of electrons. This region of space we would not find our shared pair of electrons is called our anti-bonding molecular orbital. So it's higher in energy, and it's considered to be unstable. Right, so this is our anti-bonding molecular orbital. It is considered to be like a region of space that represents a low or zero probability of finding a shared pair of electrons. Right, so once again, the bonding molecular orbital represents the highest probability of finding a shared pair of electrons, which is our bonding pair. And the anti-bonding molecular orbital represents a region of space, or it's like a concept where we would not find our shared pair of electrons.